Hello everybody. In this lecture series I'm going to talk you through how I would apply the chain ladder method in practice to a few example datasets. As I've said before, reserving is an art, not a science, so this isn't a step-by-step set of instructions, but it should be helpful in explaining how I go about selecting link ratios to predict future claim development, some quick checks I use to ensure my historical data is reliable, and that the chain ladder method is an appropriate choice, how to smooth through unreliable data, and also how to select tail factors, and finally how I check that my predicted ultimates are as reliable as possible. In this second video in the series, I'm going to explain how I go about dealing with the link ratios in later development periods, covering off how I would smooth through unreliable data and set tail factors when my triangle of data is not sufficiently large to cover all historical claims completing the policy lifecycle. So let's get back to the modelling. Let's say that we're happy that we've done the best job we can in selecting link ratios by taking sensible averages of the actual link ratios using all the tips and tricks covered in the first video in this series. By the way, if you've not watched that first video, then I recommend you circle back and watch it first to ensure you're comfortable with selecting link ratios to apply to future development before moving to smoothing through those selections. We now need to assess if we need a tail factor, as well as whether or not we need to do any smoothing of link ratios in later development periods. Remember, the later link ratios are averaged across a small number of actual historical link ratios, and so can be unreliable, even with a robust chain ladder model in place. The best way I find to make these assessments is to look at the cumulative development percentages implied by our selected link ratios, i.e. the 1 divided by m, or put another way, the x divided by y values, which we calculated in the last video. So what we're looking for is our selected link ratios to produce a smooth trend towards ultimate, and also that it looks like the development is complete at the end of our triangle. In this example here, I'd say that our selections look pretty good. We have a nice smooth trend, and we're clearly at the ultimate position well before the end of the triangle. In this situation, I would not adjust my selected link ratios, and would just move on to reviewing my results for reasonableness. That's covered in the next video in this series. As a rule of thumb, this is usually what happens in about a third of the models I run, although this could be a lower percentage for longer tail business. So let's talk now about what can happen the majority of the time, which is when I need to make adjustments to my selected link ratios using curves and or tail factors. The first case I'm showing here is where my initial selected link ratios are good and have picked up the essence of the true but unknown development pattern, but where there's still a bit of noise distorting the signal. So I get a pattern like this, where all the claims have made their way through the policy lifecycle by around about development 10, but I get a little bit of oscillation around the 100% point after that in the development pattern implied by my selected link ratios. In this example, I would normally quickly check that there's no valid reason for this oscillation, and usually there is no reason that I can think of which would explain why the claims would be acting in such an erratic way, jumping up and down from period to period. And then I would replace my erratic link ratios with flat link ratios, i.e. setting link ratios covering development periods 11 onwards equal to 1. This exhibit here shows how my expected development pattern would become in orange when I do this smoothing. What I'll find is that the ultimate I get from this model will be almost identical in aggregate to the ultimate I'd get had I left the model unchanged and erratic, but it will be much easier to justify, and I won't get odd positive and negative IBNR values in the back years. I end up taking this approach in about a third of the models I build, so again it's very common. You'll note that I've left in the improving development profile from development period 6 to 10. If I have satisfied myself that claims improve over this period in the historical data, and my model hasn't been biased by one odd origin period or a data error, then I would naturally want to keep this feature in my model. It's often the case that incurred claims can go above their ultimate position due to prudent approach to setting case reserves in the claims department, and we want our model to accurately replicate the policy life cycle, so we should keep in any features which are seen in the data and are justifiable. If instead we were to flatten out the development from period 6 rather than period 10, then our model would be biased, and we'd have implicit prudence, which, as discussed previously, would lead to incorrect pricing and capital decisions, so clearly not something we want to do. The final scenario I need to cover off, and one which occurs again about a third of my models, is where I need to smooth through unstable selected link ratios and or estimate a tail factor. The approach to both of these cases is the same, so I'll cover them off together. The first thing to do is to assess whether smoothing is required, and I do this by considering, again, the 1/m development chart. In this example, we can see that my cumulative development still seems to be moving out by the end of the triangle, and so a tail factor may be required. We can also see that the development looks a little unstable in later development periods, so a curve may be required there too. Remember, these last few selected link ratios are based on just a few actual historical link ratios, and so quite often need to be smoothed through. Note, as always, the option remains to seek more data or to use a benchmark. But let's go through the process of fitting a curve so you can see how I would approach this problem. Step 1 is to assess from where you need to fit the curve. You should have early development periods with enough data to calibrate your model and estimate something close to the true but unknown development pattern. So we generally want to use our selected link ratios derived from actual historical link ratios up to a certain point, and only then switch over to smoothing through the later development periods and into the tail. By the way, if you find that you can't even calibrate your model well for these earliest periods, then the chain ladder method is probably not the right tool for the segment you're modelling. Looking at this exhibit, what I'm looking for is where the data-driven development pattern starts to become materially unstable. Now be careful here, as we know there are policy lifecycle features such as limitation periods which can cause distortions in how customers report claims and hence will distort development patterns. We don't want to smooth through these genuine features, but if in the tail we're seeing our data-driven development profile jumping erratically, then this is unlikely to be a true feature, and so this is where we may need to fit a curve. In this particular example, I would smooth through, say, after 14 development periods onwards, possibly even 13, if I think that the 13th and 14th development link ratios are connected. The last 4 selected link ratios here are based on 4 or less historical link ratios, so unlikely to be well calibrated, and hence the need for smoothing is not surprising. So I've taken my selected link ratios from analysing our historical data, and I now want to smooth through the 13th, 14th development period onwards. Let's talk through how I would do that. Some tools will enable you to do this directly, but you could just do this in a side calculation if not. There are lots of ways you could do this smoothing, as well as lots of potential curves you could fit to the data, so I'm going to talk about principles more than specifics here. To explain what this exhibit is showing, we have the link ratios from analysing our historic data on the left hand side. I'm then including all of these points in the curve fitting process to derive 4 mathematical curves. I also have a manual entry column should I want to override the curve fitting process and put my own values in. This is where I could flatten out the development with link ratios of 1, or use a benchmark development pattern. Generally, don't use manual development in any other case, as it's very hard to justify subjective link ratio picks and may well bias your model. There are various things to consider when fitting curves. These are: where do you want to use the curve from? Which data points are you going to fit the curve to? Which fitting method are you going to use? Which curve are you going to use? And how many future development periods are you going to include in the tail? From the previous exhibit, I've decided I'm going to fit the curve from the 13th or 14th development period onwards. Next, I need to decide which data points I'm going to include in the fit. Now, this is definitely an art, but there is some scientific guidance I can give you to help you make the best selection of link ratios to include in your curve fit. It's normal to want to use the curve to smooth through link ratios in the tail, and so we should be concentrating on getting a good fit in that part of our data. It's no benefit to us having a great fit in the early development periods, especially if that's at the expense of a good fit in the tail. Insurance claims tend to develop quickly at first, as events occur in the policy coverage period and customers make claims before it takes some time for these claims to be fully assessed, agreed and settled. This is a pattern which is quite difficult to get a curve to fit to, so it's easy to just fit the curve to the claim settlement part of the development, i.e. excluding early high link ratios where lots of claims are coming in. So to allow for these 2 points, you'll generally want to exclude some of the very early high link ratios from the curve fit. You'll also want to exclude some of the later link ratios, as these are erratic and unreliable. This can be a tricky decision, although I almost always want to take out any selected link ratios which are based on just 1 or 2 historical link ratios. Removing data points from the early or later development periods needs to be balanced against including enough data points to get a reliable curve fit. Do also beware of the patchwork quilt approach of taking out selected link ratios too readily or inconsistently. Ideally, you want a long run of link ratios included in your fit, excluding the top and tail points only. However, this is generally an iterative process, which I'll go through in more detail shortly. Next, you need to decide which curve fitting method to use. Least squares regression would work, and it's the one being displayed on screen, although it will give you extra weight to your high link ratios where we don't want to use the curve, and so optimal data point inclusion is key when using this fitting method. If you use log regression instead, then link ratios less than 1 will be excluded automatically, and you can end up with a biased model if you don't counter this by excluding some of the higher link ratios, or by applying it only in situations where you have no link ratios less than 1. We also need to consider how many future development periods to use in the tail. This should take us from the end of the triangle to the point at which we believe every claim should have completed its journey through the policy life cycle. Having too high a number is not normally a problem, so the most important thing is not to cut the tail too short, as this will introduce a low bias into your model. Lastly, you need to decide which curve to use. If your data is well behaved, then you may find each curve fits well and consistently. However, in other situations the data is erratic and you have a wide range of potential curve fits. If you are free selecting your own curves to fit, then do beware of overfitting. Link ratios should trend down towards 1 as more and more claims complete their journey through the policy life cycle. This means that generally 2 or 3 parameters in your curve equation is sufficient. Add too many and you might improve your fit to actual data, but get some very odd results when extrapolating out into the tail. And don't forget that in some circumstances, the tail can be as long as the historical data used to fit it, so that extrapolation is key. One option would be to check how well your curves have fitted the actual data by looking at, say, the R-squared goodness of fit score. But do beware that this does not guarantee a good projection, only a good fit to the historical data. I often discount and don't use curve fits with low R-squared values, but I wouldn't just pick the curve with the best fit unless I was also happy with the results. It's generally a good idea to save down a few different model results using different curves to fully understand how important this decision is, and also to give you a feeling for the materiality of this assumption. Let's look at some charts to help illustrate these points. So this is showing us the same information as the last exhibit, but in chart rather than table format. I often find a picture helps us cut through all the data and immediately tells us if something looks out of line. We're looking at our selected link ratios in orange, and then the 4 different curves fitted to that data. We can immediately see that the curves aren't a bad fit, as they broadly follow the orange line, but there are some issues which are concerning to me. Firstly, note how well the curve is fitting the first few development periods. By using a least squares fit, I focus the curve fitting in the wrong place. And then note how there is divergence later in the development, where I'm more likely to use the curve to smooth. It's not apparent from the chart, but we also have a big difference in predicted tail factor, ranging from 0 to 22%, which is again concerning. Let's go back to our curve fitting selections and try to improve the fit. So, I would normally exclude the last few link ratios from the curve, as these are based on little data and unlikely to be reliable. Here I've taken out the last 4, as they all look quite erratic. I also want to take out some of the early high link ratios, so that they don't distract my curve fitting process. Here I've taken out the first link ratio. I've also changed to a log regression fitting method. As mentioned earlier, this is a more robust fitting method, and all the ratios I want to include are greater than 1, so there's no bias introduced from using it either. Because I'm using log regression, I get to see my R-squared values, and these are all north of 85%, and so all 4 curves look reliable to me. And as noted before, I wouldn't just automatically pick the one with the highest R-squared value. I'd be careful though around picking curves with very low R-squared values. It may well indicate we need to improve our calibration, or that this class is not well suited to being modelled using chain ladder. It's also worth noting that moving from quarterly to annual development can change R-squared values a lot, even though the end result of your model remains the same. So take care to ensure you can justify and rely on your curve fit. We can already see that the tail factors have got more aligned, ranging from 1 to 14%. This is still big, so I need to understand that more before selecting my model, but we're moving in the right direction. Getting a wide spread of tail factors is another red warning light which we need to be aware of. The spread isn't too bad here, but a wide spread is generally an indication that either the curve fitting process is bad or that we need to consider if the chain ladder method is the right one for us, as it's just not possible to identify the true but unknown future development pattern from the data available. In that case, we may need to seek benchmarks, source more historic data, or to change our segmentation. Again, curve fitting is often an iterative process. Sometimes you need to tweak which values are included in the curve fit to get a stable and reliable fit. You might need to remove more early, i.e. irrelevant curve misleading points, or later, i.e. insufficiently credible link ratios from the curve fit until the curves look good and so do the results. One good check when smoothing is to compare your 1 over m values, your cumulative development percentage, from the point where you need to fit the curve against each curve fit and also the selected link ratios, i.e. do I still get 92% developed after 13 development periods? Do I select curve 1 or curve 2 or curve 3? These should be close, although naturally tail factors will bias this comparison as they can't be included in your historical data. However, once you calibrate well and consider things methodically, it may simply be that you've done the best job but still can't decide between curves. In this case, it is best practice to save down the results from various assumption choices. This will enable you and others to measure the uncertainty in this decision. Let's see how this hopefully improved fit looks graphically. Now I've zoomed this chart in a lot to help us see what's going on. We can now note that the curve fit is not great for those early development periods, with big differences between the curve values. But this is fine as we don't want to use a curve to smooth there anyway. What we are seeing is much closer alignment between the curves for later development periods, where we actually do want to smooth through our selected link ratios with the curves. What I would do now is select one of the candidate curves and use the fitted values instead of the selected link ratios from the 13th or 14th development period onwards. This will amend my m values and hence my selected ultimate y values. Now it's worth bearing in mind that any curves you use are not going to be magical or specially designed for our purpose. They're just going to be mathematical curves which happen to fit insurance claims well. So don't get overly confident in their ability to predict the future for you. We still need to do more investigation and checking of results, and this will be the subject of the next video. I'd like to close off this curve fitting video with an example of less than optimal curve fitting and selection. When I'm reviewing and I see something like this, then I'm immediately concerned that the modeller has overfitted the model or that the data is not reliable enough for the chain ladder method. So what's wrong here? Well, firstly, there's some sporadic exclusion of link ratios from the curve fit. In fact, they all look a little low, and so the curve fits are likely to be biased upwards. We can immediately see that in the tail factors, which now go all the way up to 49%. Next, the modeller has included both the first and last link ratios in the curve fit. As discussed, the last link ratio is only based on one historical data point, and so is unlikely to be reliable. And by including the first link ratio, we're distracting the curve fit away from where we actually want to use the curve to smooth through unreliable link ratios. Looking at the green highlighting of what's been picked for each development period, we can clearly see evidence of patchwork quilt selection of curves, jumping from selected to curve 2 and back again, and then jumping over to curve 4 and even back to curve 2 in the tail. There's no way of justifying such variation, and almost certainly the modeler is overfitting the chain ladder here. As a quick tip, always ensure in the tool that the x is under the same curve as your tau factor. Lastly, the volatility in the 14th and 15th link ratios has been left in the model. This is unlikely to be a feature we'd expect in the true but unknown underlying development pattern, so again it's hard to justify why this selection has been made. If you finish your curve fitting and smoothing but end up with something which looks like this, then please think again about whether your selections are really appropriate. Maybe save down the results and then do a more elegant and justifiable model run, and I suspect the results will end up pretty much the same with a lot less effort. One last thing, I've not illustrated it here, but just to say, I would never use a curve for all development periods. I want to smooth through the later development periods and into the tail. I shouldn't need a curve for the early development periods. Anything odd in the early link ratios is probably a feature and needs investigating and understanding, not smoothing through. So let's remind ourselves of the key steps around curve selecting we've covered in this video. We have three options around smoothing and tau factors. Leave the selected link ratios unchanged, flatten some of the selected link ratios for later periods, or use a curve and I'll project into the tail. We should not be using the curve for all link ratios. If this is required, then maybe the chain ladder model isn't the right tool for this segment. And never ever smooth through the early link ratios while leaving the later link ratios unchanged. That odd pattern you've seen in the early development is probably an interesting feature which needs understanding, not removing. And where we decided to fit a curve, we stepped through this checklist. Firstly, we considered where to fit the curve. Then we assessed which data points to include in the curve fit. Then we thought about which curve fitting method to use. And finally, we decided which curve to apply from the curves at our disposal. Once we've done this, we will have our final m values, and hence a set of ultimates, y values, for each origin period modelled. However, we still need to check these results look reasonable, so don't stop here without doing the final step in our modelling process. This important step is the subject of our next video. So hopefully this video has helped you to see how I go about fitting curves and using them to smooth through unreliable link ratios in later development periods, and also to project how claims will develop beyond the end of the triangle by using a tau factor. As noted, the next video will cover how I go about checking that my chain ladder model is reliable and that the predicted ultimates look reasonable. You should be able to see the next video in this series on the left hand side of the screen, so please click here to move on to it now. As usual, please also like and subscribe to support these videos. Again, you should be able to see a small circle which you can click to subscribe. And do let me know your comments and feedback on these videos in the comments section below. Thank you.